Hello and welcome to SAE Tomorrow Today. I'm your host, Grayson Brulte. On today's episode, we're absolutely honored to be joined by John Barnes, founder and managing partner, The Barnes Global Advisors. On today's episode, we discuss the 30-year evolution of additive manufacturing, what the future looks like. We hope you enjoy this episode. Welcome to the podcast, John.
Hi, thank you. It's good to be here.
It's great to have you here because additive manufacturing's roughly 30 years old, and now the industry is kind of having its highlight moment. It's starting to grow and expand and go into multiple industries. To level set this conversation, how would you describe additive manufacturing?
Additive is the key part of additive manufacturing. It is adding material where you need it, as opposed to legacy manufacturing. A lot of it is subtractive, not all of it, but a lot of it, meaning that you start with a block and you remove material to get to the shape or design that you want. Additive adds material where you need it, and we call it a layer by layer process. So it's a little bit like very expensive Legos. You add Legos, you add them on top of each other. Each Lego is a layer, and you eventually you can make a very complex shape with it, and it can have all kinds of great details that are very difficult to do with most manufacturing forms.
But unlike Legos, you can have rounded edges, various different sizes, not the traditional blocks.
That's right. I think of like micron-size Legos. So a lot of them use maybe a metallic powder or polymeric powder. And so you could think of those as notionally 40 micron little Lego blocks. But you're right. You can create curved designs and very nature-inspired designs as well.
For a listener that says, okay, this is cool, is it kind of like a very large warehouse-size inkjet printer that manufactures this? Is that a fair way to compare it?
Yeah, I think the size is increasing. So, most people will see printers, metal printers and polymer printers, and they won't be that big. But they're getting bigger and bigger. And so some of the technologies do go back to the same printing technologies used for, making these large billboards. It's just that instead of having a colored ink, they have a polymer, or a glue or some other technology. And so it's actually where the term 3D printing came from. It was the predecessor for what we now know as binder jetting. And some professors from a little place called MIT came up with they coined the term 3D printing. So it was taking a 2D kind of printer, but making it in 3 dimensions. I also had an opportunity to meet the founder of Stratasys, a guy named Scott Crump. And when I asked him why he started the company, he actually said that he was really just trying to make a toy for his daughter. And being an engineer, he went and he's like, I should be able to take a hot glue gun and make a 3-dimensional shape with it. And he ended up buying one of those plotters, that you used to see in all the movies with NASA, it's this XY, very detailed plotters. Mounted the hot glue gun on that and was trying to use that as a way to, start to create a layer by layer thing. And I think he got pushed out of the kitchen into the garage, and then finally was issued a challenge that he either needed to start a company or give it up. Thankfully, he started a company. So, that's just kind of where it just came from. A couple of different people had similar ideas, and going from 2 dimensions to 3 dimensions. In the 80s and 90s, that was the fancy thing of that era. Compared to today.
There's a great story in Massachusetts where you have Goddard, and so his wife, he's building out the rockets in the backyard. No, you're going to blow stuff up, and then she ships him off to New Mexico, and then we all know what Goddard did with rockets, and then with the Lego, he was trying to build toys for his grandkids, and then from wooden blocks to plastic blocks became Legos that millions of kids around the world use. It's amazing the innovations when you put your mind to something, say, I want to build something, I want to do something, and then it turns into a business. Looking at additive manufacturing, are there certain growth industries inside of additive manufacturing? Is it the repairing of parts that you say, this is a really great use case today that you see scaling?
There's so many, and I think in a lot of sense, it's. I always make I was a big music fan growing up. And I make the analogy of additive as a little bit like walking into that record store or the CD store. If you didn't know what you were looking for, you just get inundated with choices and you just kind of walk away. And I think what people fail to appreciate about additive is, to your point, it has been around for over 30 years. It's a sufficiently diverse space. There's lots of things that you can do with it. And so, recently we were talking to a group and they were like, well, what would you recommend to small to medium manufacturers about how to adopt it? And I say it goes back to the engineer's problem, right? What problem are you trying to solve? Are we solving for cost? Are we solving for schedule? Are we solving for performance? We can do all of these things. And so, increasingly today, schedule seems to be a big deal, which is based on supply chain issues. So we've created a situation, right, wrong, or indifferent, and people are looking to kind of bolster their supply chain. So even if additive is the backup, it's still a plan, right? So then it's not always about cost, and I think, again, it goes back to, it can do a lot of things, but if you don't know what you want, then you'll do nothing with it. and I think that's a learning that we get from a lot of people. They also don't appreciate that there's multiple families of 3D printers, and maybe you need a polymer, maybe you need a metal, maybe you need a ceramic. That starts to help you narrow down which process you might want to use. Knowing what problem you're trying to solve is always a very good engineering approach.
The supply chain imbalances are only continuing. There's reports they go into 25 to 27. Are those imbalances accelerating the demand for additive manufacturing, especially around, you want to call it a repair part or a specialty part?
I think it certainly has caused people to be more cognizant of what their options are. And I was at the military AM summit down in Tampa earlier this year, and there was a 4-star general that was talking about the Air Force's needs. And he said that, and I may get these numbers wrong, but something like 80% of the Air Force's spare parts were met with a repair. And I was stunned. And he went on to say that 92% of the spare parts were met with sole source suppliers. And then 10,000 bids just weren't ever bid to. There was no supplier for that technology anymore. So when you're dealing with that kind of world, repair may be your only option because the tools don't exist to make the new parts, and for a variety of reasons. So I think that it has always been there. When I started in additive, that was actually, we were like, well, this is interesting. I mean, yeah, we could make impellers for aircraft engines, but that's going to be hard to do. And then we just tried depositing onto a steel bar with the same alloy steel, and what we got was an interface that was stronger than the parent metal. And so we were just trying to figure out what to do with this technology. And so we're like, oh, well, this could be a pretty precise repair technology. So, the directed energy deposition and now cold spray, those technologies are specifically being developed for repair for the Navy, for the Air Force, the Marines, and the Army, and in multiple militaries. So the services are definitely looking at this as a way to, solve problems that the soldiers have. And a lot of times, we get caught up in jet engine parts and airplane parts, but there's a lot of spare parts that they just need to be there. And if you don't have them, it diminishes the capability of the weapon system. So it's I had a colleague when I worked at Lockheed Martin. He was a Bradley commander in Gulf War I, and his gun was inoperable on the first day of the ground war. So he's going at full speed into Kuwait for want of like a 10-cent part. And so he was like, man, if I could have printed something, even if I made a handful of them and they kept breaking and I could replace it, it was better than my situation, which was, full speed, no gun. Fortunately, it worked out for him, so no harm.
Using that use case scenario, do you see the military putting additive manufacturing into theater?
Yeah, they already are. There's several attempts have been made, what they call almost like a MASH, a mobile hospital. So they do have these things in, I'll call it containers, and they're deployable. There's a lot of work going amongst several services around what they call expeditionary manufacturing. And so they have different levels, whether it's at a logistics base, a depot, or if it's, actually in the field. And so, one of our great allies is Australia. And there's an endeavor going on in Australia currently with the Australian Defence Force and the U.S. Marines, and they're using a cold spray technology in the field, showing how they can rapidly make wrenches and things like that to solve problems. And that's just an example. There's a variety of, all the different services are looking at this, and there's lots of interesting reasons that the military comes in. And then you think about what's also similar. So like oil platforms, very remote. It's very expensive to get parts to them. Then you think about things like space stations, and if we ever have a facility on Mars, rather than trying to accurately predict all of the spare parts that you're going to need. The next best thing is bring a spool of wire and a printer, and you can print anything that you might need. And the proviso there is it just needs to be good enough. It's not going to be perfect. So the services are definitely interested in this expeditionary manufacturing. It's a unique capability. It allows them to operate with hopefully with a little bit less of a logistics supply trail, which is obviously important to them.
Looking at, you have the Coast Guard, you have the merchant marines, and then on the civilian side, you have the large maritime container ships. There's space on those. You can convert a bedroom or a cabin, if you want to use that term, and something breaks on that ship, they're at sea for weeks. Do you see that as another great example of where additive manufacturing could add value?
I do, and a lot of these big ships already have machine shops in them. One of my favorite movies growing up was Operation Petticoat, which was a World War II story about a submarine that picked up some nurses that were stranded, and they were living in close quarters on the submarine, and somehow it needed to be painted pink, and it was this whole thing. But at the end of the day, the head nurse and the head mechanic on the submarine needed to solve a problem. She was very mechanically inclined. He was kind of this grumpy old guy, but they ended up using undergarments as a spring mechanism to do what they needed to do and save the whole sub, type of story. And this is no different. This is a new tool that we have to solve problems with. And so the shipping lines, they go weeks at a time when they're out at sea. And so it's a very similar proposition. Sometimes you just need a part. It's not a safety critical part. Using something for even a shorter period of time is better than maybe not having it at all. So I think it goes back to kind of one of the first questions you asked, and it's like, okay, well, what problem are we solving? If it allows us to be higher performance in between spaces, this is a new thing that we can do. If we're trying to reduce costs of operation, maybe that's part of it. But a lot of it is, there's a business case yet to be invented because we haven't had, I'll say, this type of solution. This solution has existed. Additive hasn't invented manufacturing. It's just a new way of doing it.
Do you view the number one problem solved is efficiency? You can increase efficiency and lower downtime?
I think that is a use case. I think that the design flexibility that you're afforded with additive can be impactful to these larger systems, whether it be weight or maybe performance. And so you look at heat exchangers. That's an area that has picked up in performance. Even on the biomedical implants, a lot of times the bone ingrowth on additively made implants are better than their counterparts. So we are seeing this adoption across these areas where the performance afforded by additive is there. It's a challenge of the humans being able to filter through and understand how they use it to get that better performance. I always draw the analogies. At Lockheed, we had we called it part unitization. So it was, how could we take, a part, a wing rib or something like that was built up of several extrusions fastened together with ribs and stiffeners. Sometimes you could just go machine that entire thing out of a piece of plate, and saves you a lot of touch labor, and it consolidates the bill of material. So it reduces complexity significantly. And this is, a furtherance of that. The part unitization is something that can be done with additive. And in the process, you can actually get higher performance out of it because you've eliminated joints, fasteners, welds, et cetera. And it's one of the areas that the space industry has really kind of gravitated to, because on some of these structures are using welded structures. And, structural engineers will look at welds and, kind of cringe a little bit. Every weld is an opportunity for, a failure. So if you eliminate the welds, you've improved the reliability of the system.
You had higher performance. Can you also use stronger, lighter materials to reduce the weight, especially as you go into aerospace? Yeah,
and this is that the complexity that comes in and makes it hard for people to appreciate additive. So if you look at some of the metal technology specifically, if we just use that as an example, they use metal powders, a lot of them, and so if you're used to using mill products that come out of a mill like bar and plate, you appreciate that aluminum's maybe $5 a pound and titanium's $20 a pound and nickel superalloys are 20 something a pound. So that's your mindset. That's what you're thinking. In the powdered world, stainless steel powder and nickel superalloy powder are $5-10 a pound difference. Big difference in performance. And so you got to look at the whole picture. The cost dynamics of how you make powder kind of neutralizes some of the cost that isn't present in how you make plate and mill product. So, one of the things that we try to teach people is, well, if you're trying to insert an additive part into a system with a certain high level of performance, and maybe it's a steel part, if you replace it with a nickel superalloy, your chances of success are higher. It's a different alloy, so it's, you got to do those studies, but strength, stiffness, temperature resistance, all of those things are better with the nickel superalloy. And you got to look at the cost of the feedstock, the cost of printing the part, and the cost of doing the post-processing. And in legacy manufacturing, a lot of the time goes to machining, and here we're using the printer. So the less material you use, the less time on the printer you use, the lighter the design. Time is money with additive. It allows you this flexibility, so you can go to higher performance oftentimes with no cost detriment. We did a study with one of my long-term colleagues, John Meyer at AppWorks, and we looked at a brake caliper. So for a car, it's an aluminum brake caliper, so it's more of a high performance application. And we just did a fairly simple study. We analyzed it. We looked at the legacy machining approach, and that's a fairly massive block, because to continue to get weight out of it was going to cost a lot of money. And then we looked at printing it with the current aluminum silicon 10 alloy for printing as a powder. And then we looked at this, what was known to be a very expensive alloy called scalmalloy, because it has a small amount of scandium in it, which is one of my favorite elements. And so everybody looks at scalmalloy like, oh my gosh, it's so expensive. And in the end, when it gives you higher performance at the part, when you resolve it at the part level, the scalmalloy part was the cheapest of them all because you required the least amount of material because it was very strong. Its specific strength was very high. Aluminum silicon 10 was more expensive because you needed more material. If you need more material, you're spending more time on the printer. Time is money. And then you had the machine design. So the machine design was still cheaper, but the printed scalmalloy design was far lighter. So if you wanted performance, you might be willing to pay for that. But as an example of, scalmalloy is 100 times more expensive than aluminum silicon 10, and yet the part made from scalmalloy was cheaper. So this is a dynamic, a lot of manufacturing engineers, very counterintuitive.
Do you see standards playing a role here if you're going to replace a hinge or you're going to replace a brake caliper, for example, like the role standards will play, so no matter what vehicle you put it on or what aircraft you do, there's a consistency across the board. You're not using a metal that's been proven to buckle under high heat, for example?
I think that there's a pyramid of need out there. Specifications, standards, data, and to another extent, sort of allowables. And so this is not a well understood pyramid for a lot of people, nor do they need to understand it. And so you do have to have a certain amount of standards. You have to have specifications that call out those standards. You have to have the specifications to create the data that can be used in an allowable. An allowable is then, the definition of it's what a designer uses as what is an allowable stress that they can meet with that material, and to get towards a certification and qualification event. And we use these terms interchangeably. They're not the same thing. Different industries, qualification means different things. But what we tell people, the process for qualification is the same. We're not actually changing that. It's the details that have changed because we're using a different tool. So these things are necessary for widespread adoption. One of my sort of pet peeves is that when I hear people are waiting for standards and specifications, because engineers write specifications. It's part of the job. I've written them. I don't enjoy writing them, but I've written them, and you can improve them. The other thing the comments that I've heard is we need to get better at doing standards in a shorter period of time. It's like, well, they're called standards for a reason. We don't use them. We don't make them in a short period of time. They are then standards. So specifications, you'll often see, letters designated a revision, and that's acceptable. That's why you have a specification. You learn something, you improve it. Standards, you don't really want to have revisions to it. There's supposed to be standards. So that's how we measure something. That's how we do a tensile test. Those are the things that we don't really want to change. Then, the activities that SAE is involved with the ITC around doing the data collection with an industry consortia that then go into what we call specification minimums, it's a very healthy activity to be doing because it's necessary. And then when you go to an organization like MMPDS that do the quote unquote allowables, all of the other things have to exist for those guys to even think about doing it. So you have to have the standards, you have to have the specs, and then you have to have the data. And what we routinely tell companies and suppliers is, and specifically the printer companies, if you produce data without a specification, it's meaningless. But if you have a specification that you produce the data with, okay, you have a high likelihood of being able to use it. If you need to revise the specification, okay, that's fine. And I learned this the very hard way. So, in my youth, I had a program with the Air Force, and to this day, I got a severe tongue lashing by an individual at the Air Force. So I learned that specifications are very important. So today, even today, people would be like, "Man, you really took a beating from that guy." Yes, I did.
It's a lesson you obviously haven't forgot, but it put you on the right path. I'm listening to this and I'm thinking about quality control. So, for example, if a part's being additive manufactured in, say, Seattle, and another part's being additive manufactured in Charleston, South Carolina, how do you ensure that quality control, since they're two different parts of the country, 7 hours apart, potentially two different supply chains, one coming from Asia, one possibly coming from Canada? How do you ensure that quality control?
Yeah, and this is something that we do grapple with, and the industry as a whole, it's certainly younger and it's not as robust as, say, like the machine tool business. So if you go buy a CNC 5-axis machine, you pretty much expect it to behave the same way in Seattle as if it's also installed in Charleston. You expect the same answer. The things you don't may change things, or like maybe you got material from a different supplier and so it behaves a little bit differently when you're cutting it. It's probably not less true today with additive printers. They're getting better. So you can kind of do two things. You can either drive a path towards, I'm saying that what I'm doing is perfect. I have perfect powder. I have a perfect parameter set. I have perfect post-processing, and I'll get the perfect answer. The other alternative is to say, well, I need this level of performance out of the part when it's finished. And so how you prove to me that it is acceptable, one relies a little bit more on the world of the perfect and a lot of paperwork. The other is a piece of paper kind of at the end. And I'm grossly oversimplifying this, but that basically says, we did this, we measured it, we broke it, and it passes. And so there's kind of two different ways of approaching this. You'll hear people talk about type certification and point by point or point certification. And so point means that you'll go in and you'll analyze a part and then validate that it's good to be used in service. Type certification is basically saying, oh, okay, if I print this material, I can use it in these applications broadly throughout the aircraft. Again, a bit of an oversimplification, but I think you get the point. It's very hard to do the type certification because it requires a massive amount of data, that says that my additively manufactured Tie 6.4 part is as good as the previous part that we're replacing it with. Whereas a part by part is much easier to do, and it's a risk adjusted path. And that's largely what you see a lot of the companies doing. They're risk adjusting their path by doing lower criticality parts, partially to prove out the supply chain, partially to prove out the specifications, where they can start implementing more and more parts safely into that system.
On an aircraft, when you put an additive manufactured part there, does the FAA step in and say, oh, wait a second, we have to recertify the aircraft? Or is there another agency that says, well, wait a second, we have to inspect?
Yes is the big answer to that question. So 100% the FAA, their European colleagues, the EASA, and other such organizations around the world, are active in trying to understand how these things impact, let's say, the flying public. So when you see a part that does make it onto an aircraft, you can bet that part has been analyzed with more scrutiny than most parts that go on an airplane. And you mentioned something, which is often overlooked. And so part of that plan can be, how visible is this part? how easily accessed is it? And so that can be part of the plan as well, which is saying, well, we've demonstrated that this part has these types of strengths. But if it's a highly visible part that's easy to get to and easy to inspect on the airplane, then that helps reduce the risk as well. So, it won't be one or the other. It's a big ball of complexity. You've got to show that you've got a controllable process, but you've also got to show that I can find this part. I might do an inspection program with it, and maybe that's on aircraft, and maybe it means removing it and doing a post or an off aircraft inspection. And then I can put it back on, and whatever I'm doing, I'm paying a lot more attention to this part than I would have to the part that got type certified with the aircraft.
Does it get to the point in the future where the FAA or another regulatory agency regulates additive manufacturing, where it has to go through a certain step of standards or processes before going on the aircraft, where this is the process that you have to follow?
Well, the usual answer for an engineer is it depends. So I'm going to throw that out there. It does depend a lot on the criticality of the part. So certainly with safety of flight parts, that yes, it's those follow a very tried and true path. And then you get into all the other ones. And so whether it's the military or the FAA, could be the National Nuclear Regulatory Groups, whatever regulatory group dominates, they will have a policy for how to adopt additive. And it's incumbent to have, what makes life easier. It goes back to the more we have specifications and the more that they follow a routine that we're familiar with. So, once again, referencing the SAE AMS specifications, the FAA is very comfortable with those, that they understand that it's a process that they get. So when AMS now with the AM committee is using a similar, I'll say, thought process, it gives comfort to the FAAs that, the similar process is being utilized. And so we've got the best answer that we're going to get. That doesn't mean that it's automatic that the FAA is going to give its approval. But, these things are complex. And so you can't just create a specification. You can't just create data. And it's I would say a frustrating and rewarding activity to serve on the AMS committee, because there's a lot of complexity, but you also have a group of very smart people that are volunteering their time, and we learn from each other. Part of that balloting process is I can see what other people are commenting on, and I can have my own comments, and a lot of times I can gain clarity through those conversations, and routinely we arrive at a better piece of paper, at the end of it. The process that you go through is critically important, and it is a team sport at the end of the day. Additive, and that is generally what one key learning for people is that additive is inherently a team sport, more so than most manufacturing technologies. So you need your materials people, you need your structural designers, you need supply chain. All of these people have to come together if it's going to work.
You look at team sports, is that what you're developing as at Neighborhood 91 in Pittsburgh on 200 acres? You're bringing multiple individuals together from multiple disciplines, say, okay, we're going to build the future of additive manufacturing in Pittsburgh. And is that what you're doing? And then I want to on the backside of that, is that additive showcase moment?
So it very much is a team sport. And I find that, probably the best example in my career of a rising tide floats all boats. So this is, the Neighborhood 91 is, for those that don't know, so this is a 200-acre campus at the Pittsburgh International Airport, and it is a production campus. So its focus is production, not research and development. We have companies that are coming together to co-locate the supply chain. So this isn't a massively government-funded activity, or kind of propped up by government. These are actual for-profit entities that are coming together because they can arrive at a better answer together than they can individually. And one part in the supply chain for additive is that there are lots of steps in there, and you're shipping these parts around, for heat treatment or mechanical tests or inspection or, whatever the reason may be. And so we did analysis and showed that maybe the average part on metal side goes through 70 manufacturing days. If you're co-located on campus, that might come down to 20 manufacturing days. So that means that your working inventory is lower, you're getting paid sooner. It's a whole lot less time that things are moving around. also more sustainable. We're not shipping things around and burning fossil fuels or creating CO2. So the idea behind Neighbor 91 is that we're creating those companies that want to come together to create a better outcome. So we've got parts producers, we're talking to powder producers, we're talking to manufacturers, and then the services are coming in with machining capability, with inspection capability, with testing capability. We're fortunate in Pittsburgh because we've got a legacy of manufacturing. It's known for manufacturing. The workforce, as I call it, is the new natural resource. So we have a workforce that likes manufacturing. Additive is a very clean manufacturing, so we're seeing interest from younger people, and a lot of them don't even associate it as being manufacturing. It's just cool, and let's just let it be cool. The point is we need more brains. The more brains that are involved in manufacturing, the better we're all going to be. Because what the U.S. does well is this high-end, high mix, low volume kind of manufacturing, specialty manufacturing. We when it gets to high volume and lower cost operations, then we let our friends overseas kind of deal with that situation. So Neighbor 91, it's probably one of the best projects that I've been involved with. It is a big deal. It's a big deal for the region, but I think it's a big deal for the U.S. because if it works, when it works, it can be replicated elsewhere, maybe with slightly different flavors. And also in Pittsburgh, we have fantastic universities. We have this development called Mill 19 that Carnegie Mellon operates. We've also got, which sits inside a development called Hazelwood Green. That is also a 200-acre development. But its focus is a little bit more at the development side. So you invent things at the universities, University of Pittsburgh, Carnegie Mellon. You go to Mill 19, you go to Hazelwood Green to develop it. Neighborhood 91 is then the final mile. That's the production side of things. And so when you think about innovation and the innovation system, if it can't be produced, it's not innovation. It's just interesting. So this is a tough reality for inventors. You have to be able to produce the thing that you've invented. Somebody needs to write a check for it. That's what makes it innovation. And I think this is where the Pittsburgh region is a little bit unique in that we've got effectively 400 acres under development doing just that, development and then production.
Could you share some examples of companies that are currently operating at Neighborhood 91? Sure.
The anchor tenant is a company called Wabtec, and as they say, they're probably one of the biggest companies that you know of that you can't mention by name. But they make freight trains, locomotives, and in Europe they're mostly known for transit, so people movers. So in the U.S. They make a lot of the locomotives that you'll see, and of course here in Pittsburgh I can walk down about a quarter mile and watch their product roll by every seems like 15 minutes. So they're using additive at the campus to manufacture parts for not only new builds and new designs, but also for spare parts and for their customers. So immediately that they moved on the campus, they started exporting parts to Europe. And so that's the first use case. And they're using a very large metal 3D printer made by SLM Solutions called the SLM 800. And it has an 800 millimeter tall build envelope. So, quite large for additive. People who are in legacy manufacturing will still consider that to be maybe small, but it's large for us. And they've got the first of the kind installation of the SLM 800 with something we call the AM hub, which is a very automated process for maneuvering the powder. So it's the first installation outside of Germany. So it's a very advanced installation. The second tenant that we had is a company called Cumberland Additive, and they're a legacy contract manufacturer. They've been based out of Austin, Texas, and this is their expansion facility. And they're focusing more on the light alloys. Their specialty is aerospace, defense, and oil and gas. So they're building out their space currently. They're looking to a June opening, and we're actually hosting the Aim Higher Defense Manufacturing Community event that University of Pittsburgh's sponsoring out second half of June. And then we've got two other younger companies coming in that are active in advanced coatings, and one has a completely new way of making powders that doesn't involve atomization. So we can't release those names yet until the lease is signed, but the first building is effectively full with those 4 companies, and we're looking at starting the second and third buildings later this summer.
It's fantastic. Neighborhood 91's growing, and Wabtec, I'm very familiar with Wabtec, and I want to give a shout out to Wabtec because they're making really cool, fully electric locomotives that are being built there in the Pittsburgh region. So go Wabtec. John, how do you see additive manufacturing growing over the next decade? Because it seems what you described, Neighborhood 91 could be that catalyst that can spur a whole industry because you have a lot of land and that could eventually possibly span to other states and other countries.
I like to joke that I'm an engineer, but I'm a pocket economist, so I pretend to know things. But cost has been the thing that holds it back. And it's true of, the first plasma TVs were thousands of dollars and now they're, $200. So this is also true with additive. The machines, the printers are becoming more productive, which helps get the cost out. When we do facilities like Neighborhood 91, where we solve some supply chain issues and get the bottlenecks out, that also helps reduce cost. And if you reduce cost, your application space grows. So the parts that were maybe critical or, borderline in terms of a cost improvement, the more I improve my cost basis, the more I can gravitate to more parts. And a little bit, this is good timing, with the president's recent announcement around AM Forward, and that's the hope there is that the OEMs will release more part numbers. With the part numbers becoming available, the printers becoming more productive, the supply chain becoming more efficient, it should make that ability to have more part numbers more available. So all of this snowballs at the end of the day that more parts is goodness. More people, it de-risks the whole situation for the manufacturers that are out there. They're not hedging on if there will be parts available for them to bid on. There will be parts for them to build on, so they'll need to recapitalize with modern equipment. So the whole thing kind of feeds on itself. It's a healthy system. It's not a race to the bottom to get to just lower cost. This is still a situation where we can create a much better situation for everyone if we kind of get in the boat and row together. And so far we've had instances of that, but it's mostly been on development. Lots of companies come together. SAE ITC is a good one. A lot of companies came together to pool their data to support the specifications, the AMS committees, etc. So I'm highly optimistic that the combination of these things are coming together, and it's a little bit what the U.S. is good at. I lived overseas for a bit. We have a bit of a reputation as being cowboys and this and that, and fundamentally it's true. It's about the creative destruction economy, but it's just it's how we roll. And it creates somewhat of a healthy environment. It's difficult to exist in sometimes, but I think this it makes for a very competitive landscape, and competition at the end of the day is a good thing.
Competition's a great thing. And putting together what you said, what is the future of additive manufacturing?
A, I don't know. B, I think that it's truly limitless in terms of what people will do with it. And what we're seeing now is we're already seeing hybrids of different types of additive technologies. We're seeing hybrids of legacy manufacturing using additive. So, the mix and match piece hasn't really been played with too much, and I see that as a huge part of it going forward. Lots of people have been using additive, for example, to print tools to cast into. Okay, so now what if we add pieces to pieces of plate or forgings and then forge them? We can get very interesting shapes. So again, people have played with it, but it hasn't transitioned into production. But we are seeing now, with more engineers becoming more familiar with how to design for the process, we're eliminating one of those mental obstacles, because if we can design for it, we can do design for manufacturing. We can get, we're not adding cost in for without good reason. And that's a big deal. So the productivity of the machines are getting better. So I think we're going to have more options. We're going to have better productivity. We're going to have a smarter workforce. And as more of the existing workforce understands how additive works, but comes with it how to make parts. And we've got this emerging workforce, which is great. We've got all these college graduates coming out. They've already they already know how to do additive, but they're still learning how to manufacture parts. I was struck, actually, I was at Purdue University, which is, of course, my alma mater. With your student ID, you get a certain amount of copies at the copy center. You also get a certain amount of filament so that you can print your own parts. So that was pretty cool. So the future, I think is very bright. It continues to grow. It's by most analysis, the industry keeps growing at 20% plus per year. It's been that way for the last 5 to 10 years. It's maturing from a prototyping technology into a manufacturing technology, but it's always gonna be good at prototyping, and that's a good place to exist. The more it moves into mainstream manufacturing, though, I think is good for everybody because it allows these lighter designs. It allows a more sustainable path for us, and generally being smarter is always a good thing. So I think, it does encourage people to get smarter about what's possible.
Additive's clearly a growth industry. It's been around for 30 years, and the next 30 years, as you rightfully said, will be bright. And as we look to wrap up this super insightful conversation where I learned a lot about additive manufacturing, and as well as our listeners, what would you like the listeners to take away with them today?
Well, I think that manufacturing is a great industry to be in, and it's not what a lot of people think. I think the other piece is that everybody can participate in manufacturing. One of the things that my firm, we believe very strongly in is we talk about engineering, we talk about manufacturing using certain language, and we've learned that when we talk about it with a different language, more people get involved. So there's really, we have a large population sitting on the sidelines not engaging with manufacturing because they believe it is a certain thing, of which I don't think it probably is. Long story short, in the height of the space race, in the 61% of engineering degrees went to women in the United States. So half the population's not contributing to this big problem. Today, that number is about 20%. So it's gotten better, but at 60 years in, or however much time has passed, not huge improvements. So we're very interested to see more brains come into the picture, because we find that this diversity of thought, the team approach, is actually going to carry the day. And this is something that I think Americans and their allies are just always better at. We're always good at teaming. When the chips are down, you got to count on your friends and your mates, and that's how you progress things. So hopefully my appeal is that people will encourage younger people to get into thinking about manufacturing, and not the way that probably our parents would have thought about it, and that it is for everybody. It's not a male exercise, not a female exercise. It needs both. That's certainly my hope, that we're very open to that, and I find that the additive manufacturing industry is a fairly open place. Still, mostly male dominated, but there's, I would say, significantly more female participation than in some of the industries that I've seen previously. So I encourage people just to get involved. It is actually a fun industry to be a part of. We just got back from one of the big events in North America last week, and everybody's hoarse from talking because we haven't seen each other for a while. But we had a good time. So I would encourage people to check it out and get smart and just get involved.
As John said, manufacturing is a great industry to be involved with, because today is tomorrow, tomorrow is today, and the future is additive manufacturing. John, thank you so much for coming on SAE Tomorrow Today. Really appreciated it.
Thank you. I'm glad to be here.
Thank you for listening to SAE Tomorrow Today. If you've enjoyed this episode and would like to hear more, please kindly rate, review, and let us know what topics you'd like for us to explore next. Be sure to join us next week as we sit down with Ytricity CEO Alex Grusin as he explains to us how easy electric vehicle wireless charging can be. Just park and charge.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.